So essentially, this story that we're following in this course has two major challenges. One is the specification burden, which again, as I've said, I'm postponing until starting next week. And then computation, we're trying to talk about those aspects with MCMC last time and today. And we agreed just before breaking that when theta is a vector of length k, each of the posterior and the prior and the likelihood are k-dimensional probability distributions. And so it's going to be hard to work with the k-dimensional posterior. So people marginalize and work out the k separate marginal distributions for each of the elements of theta, but each of those is a k-1 dimensional integral. And we recognize that there are k of these k-1 dimensional integrals. So that's a lot of integrating in high dimensions. Prediction, the basic equation for prediction, integrates over theta also, so that's another k-dimensional integral. The basic equation for inference has a normalizing constant in it, and that's another k-dimensional integral, if you didn't know how to normalize things. And we haven't talked about computation in decision making, but the expected utility, it also integrates over theta, so it's another k-dimensional integral. And if the action space is large, you'll have to compute or approximate this integral many times in order to find the best action. So here's an example of variable selection in regression, one of the basic topics that people have struggled with for decades in statistics. I have a single quantitative yi, so the yi lives in the real line, and I model it as a linear function of a bunch, let's say m, of predictors, x1 through xm, that may be continuous or dichotomous or on some other scale, and that's the surface that describes the nature of the predicting part, and then there's leftover that we haven't explained, and that gets stuck in what people traditionally call error term, which is usually thought of like II draws from a normal distribution with mean 0 and some variance that you have to learn. So if you were trying to pick well, if you were given m of these predictor variables to use in the regression, it turns out that it does not follow at all that you should use all of them. It turns out, for prediction purposes, in fact, there may well be a number of subsets of that set of m predictor variables that lead to better predictions than the model you get by using all of them, because in effect, it's a kind of a you're trying to sharpen the accuracy of the predictions by getting rid of the x's that just contribute noise to the overall story, because that will the noise x's in there will tend to make your predictive uncertainty bands wider than they need to be. Well, this is at one level it's a good thing to think about, but at another level we're in trouble, right? Because with m things to choose from, all the way from the empty set consisting of none of them all the way up to all of them, there's 2 to the m subsets, and so script A, if you're just using the actions as which subset of these regressors should you use, has 2 to the m actions to compare, and 2 to the m is big, right? When m is not even that big, we work all the time now with problems where m is on the order of 500 or 1,000, but even if just looking at 2 to the 100th is already 10 to the 30th models that you would have to compare. So that's on the order of 10 to the 30th actions to compare, actions to choose among. Pardon? Oh yeah, switch back, thank you. That's already, with current computational facilities, that's already too large to do a complete enumeration of all 2 to the 10 to the 30th of those choices and figure out which is the best one, for example. So there's going to be some serious computational problems in trying to maximize expected utility as well. And the standard thing people do when that space capital script A is too big is they conduct some kind of search through script A, looking for elements, actions, possible actions in A that lead to relatively high expected utilities. And so basically we're in a standard problem in computer science and other fields. You have a particular function that you want to maximize over a set of possibly very large set of inputs, and you don't have enough time and money to exhaustively enumerate them all. So you use some sort of method like stochastic or non-stochastic optimization to try to find good choices. Everywhere you look in this paradigm, there are potentially nasty computational challenges ahead of us. When k is small, we spent a day or so on this before, when k is small, sometimes all these problems go away if you can find that magic thing we called, if you can find a conjugate prior to the sampling distribution, TIST for short, in your problem. And so you may recall an example of that was when the likelihood function in the heart attack case study, AMI binary outcome study, when the likelihood function looked like, for theta given the data, and the background looked like theta to the s times 1 minus theta to the n minus s, where s was the sum of the ones and zeros. So the y vector y1 through yn, all of those things, each of those y's was binary, and s was the sum of the y's. And you recall that we were able to not have to worry too much about the we didn't have to worry too much about the integrals because that particular mathematical form had the property that when you normalize it, it already is a probability density. And moreover, the product of any two such densities is another one. And so that means that if we choose the prior distribution to have the same mathematical form as the likelihood, then the prior and the likelihood and the posterior all are from the same probability distribution family. And in effect, you only have to learn how to do that integral once because you then just have that same family of densities each time. So sometimes when k is small, all these problems go away if you can find a conjugate prior to the sampling distribution in your problem. So here, then it turned out that p of theta given b equals a constant times theta to some power 1 minus theta to another power for alpha and beta positive, namely the family of beta densities has the property that p of theta given the data set, the posterior, is a member of the beta family, and the prior can be chosen to be another member of the beta family, and the likelihood was another member of the beta family. And so that made all the computations easy because we only had to crack the beta family once and then you just use it over and over again everywhere you look. But conjugate priors only exist for a small subset of real problems. I'll just say real problems with generally small k. And so we need, thank you, yes, we need another more general computing method. And that's where MCMC comes in. So in a big picture sense, that more or less catches us up with where we were last time. We started out understanding that we had to specify these ingredients, and once we specified them, there was one equation for inference, one for prediction, one for decision. We started learning how to calculate in the inference equation in situations where we had a conjugate prior. We did that about two times ago, and did some examples of that. We did the Bernoulli likelihood and the Poisson likelihood and the Gaussian likelihood, and we found conjugate priors in all those examples. Then we started looking at the NB10 data, and that was a data set that was not well fit by a Gaussian. Instead, it was a data set with much heavier tails than the Gaussian. So we thought about the idea of using a t distribution as the actual sampling distribution and allowing the degrees of freedom to be unknown. And so the example we were working with last time was yi given mu, sigma squared, and nu, and the background information are like IID draws from a t distribution on new degrees of freedom centered at mu and with a scale parameter sigma squared as I runs from 1 to n. And then, of course, the other part of the model is you have to put a prior. And so mu, sigma squared, and nu has some prior. I should have said given B has some prior on those three things. So this was the NB10 data set. And already that's a problem with k equals 3, so that's not huge. But it's already a problem with no conjugate prior available, because with unknown degrees of freedom, nothing good happens, it turns out. And already, to visualize that entire Pasteur distribution, we would have to figure out some method for visualizing in 4 dimensions, because we'd have one axis for mu and one for sigma and one for nu, and then the density would have to be in the 4th dimension. And you can actually do that with a kind of point cloud of samples from that 3-dimensional distribution. You could plot that in such a way that the places in the point cloud that are higher density than others, because there's more sample points there, you could paint them red, and the ones that were less frequent, you could paint them some color that fades off to not being there. So you can visualize a 4-dimensional thing like that, but it's with some difficulty. And in any case, the thing that mostly interests us in this model is the sigma squared and the nu aren't really that interesting to us. It's the mu, because mu represented the true weight of the block of metal NB10. And so we're really interested in the marginal Pasteur distribution for mu, and we'd like to, as people say, marginalize over those other parameters, integrate them out, and get the story for what's going on with mu. And then it's also interesting to look at the other parameters as well. So that's where we were at the beginning of last time. And then I think I'll try to take us through, remind you a little bit of some of the trees in what we did last time as a way of getting back into the NB10 data set. So let's go back to the course web page and pick out the simulation-based computation guy and download that to my desktop, for example. Okay, thank you, yes. Download that to my desktop. And we can scroll back through that for a while. So we agreed at the very beginning that you can, conjugate analysis is great when you can do it, but you can hardly ever do it. So now we need a new way. And we figured out a new way by noticing, first of all, that this important thing that that Metropolis and Ulam pointed out, that anything you want to know about a probability distribution, no matter how high dimensional that distribution is, as long as its dimensionality is finite, anything you want to know can be learned to arbitrary accuracy by A, having a method for drawing identically distributed samples from that distribution, and B, having enough time and computation speed to draw a lot of samples from that. And the more samples you draw, the more accurately you can learn whatever it is about that distribution you're interested in. So observation number 1, anything you want to know can be learned by figuring out a way to sample from a distribution. And so the distribution we're interested in sampling from here we want to sample from the joint Pasteur for mu and sigma squared and nu, given the data and the background information. So that's our target. And so Metropolis and Ulam and his other friends said, all right, if you can figure out a way to draw identically distributed samples, that means little vectors of length 3, each of which has the first component is a mu draw, the second component is a sigma squared draw, the third component is a nu draw. If you can figure out how to make lots of draws from that distribution, then they will tell you how to summarize the Pasteur in all sorts of interesting ways by making those draws. And we saw how to do it ourselves. If we could figure out how to make the draws in an IID fashion, And I should have mentioned also that there will typically be, in addition to the parameters in the model, there'll typically be other functions of them that you're interested in as well. For example, I don't think very well on the variance scale. I think more readily on the standard deviation scale, which is the square root of the variance. And then we would also be interested in making a draw from the next data set, the next observation, y star. We could call it a predictive draw, for instance. So if we could make the draws in an IID fashion from this distribution, then this would be something that we called the Monte Carlo data set last time. And each draw from the distribution would give you a number here, a number here, a number here, and then the next draw would be another number here, number here, number here. And so if you wanted to keep track of what's going on with sigma, what do you simply do to those three numbers to get an idea of what's going on with sigma? Ignore the mu, ignore the nu, and take the square root of the sigma. And so if this number was sigma 1 squared star, this thing here is just the square root of sigma 1 squared star, or sigma 1 star. And similarly for the other columns. And if you wanted to know about mu as an element only of this three-dimensional distribution, ordinarily we'd have to integrate over the other two. But look, having sampled from them already integrates over them. In other words, like we noticed last time, to focus in on mu, all you have to do is get a piece of paper and cover over the other columns in the Monte Carlo data set. And the marginalization problem, which was going to be one of those k minus 1 dimensional integrals, is completely solved. Moreover, well, in particular, if you wanted to know about the mean of that marginal distribution, you just take the mean of these draws, mu bar star, and that's your Monte Carlo estimate of the mean. Standard deviation, similarly, S star sub mu, we could call it, I guess, and you could plot the density, and that gives you an estimate, a simulation-based estimate of the marginal posterior for mu, given the data and the background information, and just anything you want to know. It's really right there. If you were interested in the correlation between mu and sigma squared in the posterior distribution, what could you do? Ignore the new column and compute the sample correlation between those two columns. Anything you want to know can be learned here. And the whole thing is, if we let little m stand for how many replications there are, all you have to do is a little bit of calculating to figure out how large little m needs to be in order that your accuracy on these things is what you want. Because each one of them is now going to be a noisy estimate based upon random sampling, and so we're going to want to use a little bit of math to figure out how many iterations we need. So if we could draw in an IID fashion, that would be how we would solve all the integration problems here. If IID is not possible, then we have this thing called Markov chain Monte Carlo. So we try to bring in draws that come not from an IID white noise process. If these were IID and you took these numbers here and plotted them in a time series where the horizontal scale was iteration number, which acts like time unfolding. Think about getting one iteration every second. So it goes 1 second, 2 seconds, 3 seconds, and so on. If it really were white noise, you could think of that as a time series of these numbers here. You could plot mu star 1 right at the first one and mu star 2 and link them together with lines, for instance. That would be what we're going to call a white noise time series, because the draws are completely IID. If the posterior mean was right about there, and if the posterior distribution for mu looked like that, then what would that white noise time series look like? Would there be any trend or pattern to it? No, it would just be completely like what my father used to call shooting at the side of a barn. It would just look like there's nothing, no pattern, nothing interesting going on there. So if IID were possible, then we could think of each column in the Monte Carlo data set, not the Markov chain Monte Carlo data set, as like an IID or white noise time series, and we can use basic formulas for IID random variables to work out how large the number of monitoring iterations has to be. So if IID is not possible, then we have to use MCMC instead. And the way MCMC works is that the MCMC data set has a slightly more complicated structure than before. There's a column, still a column, all the columns are still the same, mu and sigma squared and nu, and the derived quantities sigma and y star, for example. But now in iteration 0, that's a thing called the initialization of the Markov chain, because you have to start a Markov chain somewhere. So initial values right there. Then from 1 to capital B, there's a period called the burn-in. And the idea was, I can say the words out loud again last time, like I did last time, the Metropolis et al. Idea, not the Metropolis Ulam idea, but the Metropolis et al. With Edward Teller and those other people, idea was to try to build a good Markov chain. Now, we spent some time last time working out what a good Markov chain was from our perspective, and a good Markov chain was one that had a long-term or steady state or equilibrium distribution. After a while, it settled down into a regular pattern in which it was visiting all the states that it lived in with a regular pattern. And so that nature of those visits was, if we looked at the relative frequency with which each of its states was visited and made a density out of that, that would be called the equilibrium or stationary distribution of the Markov chain. So their trick was to try to find a Markov chain whose equilibrium distribution is this posterior distribution. Because then, even though we can't make the draws in an independent identically distributed manner, because Markov chains have a dependence on where they were a minute ago, even though we can't make the draws in an independent identically distributed manner, if we can run the Markov chain for a while from some starting point and get to the equilibrium distribution, and we can guarantee that that distribution is the correct posterior, then we can at least make identically distributed draws from the posterior. And so the basic idea is that you run the burn-in period until you reach equilibrium, burn in until equilibrium, and at equilibrium, you're actually sampling from that distribution there. And then from that point on, from rows B plus 1 out to B plus capital M, you do the thing called the monitoring period. And so what we do with the initial row and the burn-in period is we toss it away. And now we have a column of mu stars, just like we had over here, and a column of nu stars and a column of sigma squared stars. And these are now identically distributed draws from that posterior that we're interested in. They're not independent now because of the Markov thing, but they are identically distributed, and that turns out to be all you need from this posterior that we're interested in. And so all the usual things apply for solving all the integrals that worked out for the Monte Carlo idea when they were IID, except that now these things are dependent time series. They're not white noise anymore. And remarkably and interestingly, that the fact that they are time series, that they depend on previous values, does not affect the validity of the sampling process. We are correctly sampling from the right posterior distribution by definition of having built the Markov chain to have that distribution as its equilibrium. But what it does affect is not the validity, but what people call the Monte Carlo efficiency of the process. Generally, what happens is that if you draw these columns as time series, what they end up looking like is series that are strongly dependent on themselves in the past. So if we think instead of what the time series would look like for the parameter mu, so now I'm going to make, this is going to be an MCMC time series plot. This is again iteration number t going this way, or I, whatever you want to call it. And now, if this is the right posterior distribution, and this is the posterior mean, and we've reached equilibrium, then what the draws are going to actually look like is one of the standard ways they look is like this. The series, instead of looking like it's just shooting at the side of a barn, it remembers very strongly where it was a second ago. It hardly moves anywhere each time, and it moves around. And so that's an example of the kind of output you get from an MCMC time series plot. And people call this a strongly positively autocorrelated time series. And what's meant by that is if I take the the column of values mu1, or I'll call it mu star b plus 1, so we're working only with the data values down in the monitoring part now, and I go down to mu star b plus m. And now I simply, let's see, what I'm going to do is I'm going to cut things off at mu star b plus m minus 1, and then I'm going to put mu star b plus 2 right here, and down to mu star b plus m right there, and drop that row out. So I take the copy of the time series and I move it what they call, the time series people call one lag. I look at it not at time b plus 1, but instead time b plus 2, and not at time b plus m minus 1, but at time b plus m. And if I tried to line it up, the last row doesn't line up because I don't have the value there. So I just drop that out now. And now I simply pass that new data set, which is of length capital M minus 1, I pass that to the little correlation function inside R. That creates what people call auto correlation function. That's the auto correlation of this time series with itself at lag 1 is what people would say. So this is the lag 1 auto correlation. And naturally enough, if the series, each time you get a draw from the Markov chain, you get a little bit of new information and a lot of old information, because it basically is going to give you a number quite a lot like where you were a minute ago, then would you expect this autocorrelation to be positive or negative or near zero? Positive. And unfortunately, if the thing isn't moving around well, this is an example of what people call poor mixing of the output of the chain. If the chain is mixing badly, it's going to correspond to, let's call this thing row 1 hat. Let's call it that, the estimated autocorrelation at lag 1. Then we're going to find that row 1 hat is large and positive. And by large, of course, I mean near plus 1, because you can't get bigger than 1 in a correlation. So that becomes potentially one of the challenges of the MCMC idea, because we're not getting a full, completely IID piece of information with every row, and because the series has a strong degree of memory with its past. Remarkably, that does not affect the validity of what we're doing. You get the right answer, but you just get the right answer more slowly with respect to how long the monitoring period needs to be. And as I mentioned last time, our principal method for solving that is simply going to be to trust that our computers are fast enough that we can take a lot of draws, and then we need to come up with a measure of the Monte Carlo accuracy in this time series setting, and I'll show you a formula today that helps with that. So that's basically what we did last time in the big picture sort of sense. I showed you a little bit about how the Metropolis algorithm works. And from that point on, we're not going to pay a lot of attention to how the algorithm works, because we're going to take it as something like the engine in your car. If you're not very handy as a car mechanic, it's just a box, and it makes your car go, and it's valid. It works. And you can yourself change the efficiency of it a little bit by driving a little faster or slower in terms of where efficiency is gas mileage, for example, or you can change the efficiency maybe by putting in higher octane or lower octane gas or some things like that. That's going to correspond to us perhaps making slight adjustments in how we use the black box. But mostly we're going to treat the MCMC engine, sampling engine, as a black box that we don't have to worry about anymore. And the reason we're going to do that is that with the computation problem solved, we can now begin focusing on the much more interesting question of, do we have a good model for the data? How can we know if we have a good model? Once we've discovered that the model isn't any good, how can we figure out how to find a better one? And these are all those questions that start arising when you think about what earlier I called the specification burden. So it was a great moment in the history of Bayesian work when MCMC came along and freed us from having to focus only on models that were easy to compute in. You know that old story about the drunk looking for his keys underneath the lamppost because that's where the light is strongest. The analog of that in science for a long time in Bayesian computation was we only used the models that we could compute with. And so it was like having to always hang around right underneath the lamppost, because we didn't know how to see things very well when we got away from the lamppost. But now now the sun is shining all day long. There aren't any lampposts that you have to hang around near, and we can just focus on the real science of finding good models. So that's what's so great about MCMC. It frees us up from the part that was holding us back and allows us now to actually get some good work done. So let me remind you of what we did last time with WinBugs, and then I'm going to show you how to do that instead with our JAGs, for those of you who are prefer to work in in a non-Windows environment. And by the way, since R runs in any environment you like, if you find that you like R JAGs better than WinBugs, even if you use a Windows machine, you can run R JAGs inside R on your Windows machine instead of using WinBugs. But I find the pull-down menu aspect of many things that I want in WinBugs to be particularly handy, so I'm going to continue to use it in here. So I fire up a copy of WinBugs, and I go to the web page. Oh, thank you. Go to the web page, and I grab the model, and I copy and paste it into a window inside WinBugs. So I say new, please, and can I please put that stuff in the window? And as I showed you last time, the default font is always too small for my eyes, so I prefer to have it be in 12-point font. That's going to make it a bit easier for you guys to see things as well. So that's my model file. And we talked through the syntax of that last time. Would anyone find it useful to talk again about the syntax of how you specify a model like this? The model specification in RJAGs is identical. You take the same exact model as you use in WinBugs, with one exception. Up here in the very first row for RJAGs, you type in the word model right before the curly left brace. And in fact, if you do that in WinBugs, it won't complain. It understands that as well. But for some reason, Martin Plummer needed that word there to really make things work. I don't really know why, but that's his story. And so you remember how you do it. You write a loop across the data values, which defines the sampling distribution. And then, of course, WinBugs is going to turn that around and think of it as a likelihood function in the parameters. You say to yourself, well, what are the free parameters in that sampling distribution? They're mu and tau and nu. So each of those things has to have a prior distribution. And we went through the logic last time of how I chose these particular priors to be relatively not having much information content. So each of them was diffuse in the direction of each of those separate parameters. And you recall for things that have to do with the normal distribution, and the t is related to the normal, as you know, anything to do with scale in the normal family in WinBugs and therefore also in RJAGs is the scale information is expressed not by means of the standard deviation, not by means of the variance, but by means of the 1 over the variance, that thing that people call the precision. And the symbol for that is usually the Greek letter tau. So here I'm putting tau right in there as it has to be, and then I'm putting a prior on tau. But then I really am more interested in sigma, which is 1 over the square root of tau, because then scale comes out on the scale of the data where I understand. And then the last line here, I showed you last time how this line here simulates from a draw from the predictive distribution. Essentially what it does is it takes a mixture of the posterior distribution as the mixing weights, and it gets that by taking each draw from the posterior. And then the thing it mixes over is the sampling distribution. And so that's what this says. Make a draw from a t distribution with mu and tau and nu as its parameters, and then what you're going to be doing is averaging that over the posterior to get a draw for the predictive distribution, just like I showed you last time. So this is a nice syntax for creating predictives. And predictives, as we're going to see more and more in the rest of the course, predictives are vital in Bayesian work because they allow us to do model comparison. Good models make good predictions of observable data. Bad models make bad predictions. That's one of the main ways we know whether we have good or bad models in statistics. And so this is one of the great advantages of the Bayesian story. Predictive distributions are relatively easy to compute, and that means that we have a powerful tool for deciding whether models are good or bad. Then we're going to need a file for the data. And so I start another new file and bring the data in. I go back to the web page and pick up the data file. And as we talked about last time, it has the same, as we noticed last time, there's very strong resemblance between syntax in WinBugs and RJAGs and the syntax in R. So here, this is the same sort of list structure that gets used so often in R. Let's make it a little bigger. Let's go all the way to 12 point. Okay, so there's my data set. And then lastly, you have to start the markup chain somewhere, so we need a little file with initial values in it. And this can be quite small. So I go back to the course web page and grab the initial values. And put them there and make them a little bigger. And then in the menu-driven world of WinBugs, I grab under the model pull-down menu, I grab a specification tool, and I foreground the model and hit the check model button. And although you can't see it for some reason down here, maybe do I need to go like that? Yeah, there we go. It says model is syntactically correct. Then I foreground the data and hit the load data button, and it says the data have been loaded. And that allows me to hit the compile button, and when it's done, it says model compiled. Then I foreground the initial values and hit the load inits button, and it complains to me that this markup chain contains uninitialized variables, namely the y.new, and so I hit the gen inits button to finish initializing all the nodes in the graph, as people say. And now that I'm done and I get this great phrase model initialized, which is what I want, I can kill off the specification tool and pull down from the model menu. I can get an update tool. I'm about to do some updating without having set up any monitoring yet, and so that corresponds to the burn-in part of the story, because I'm going to do some sampling from the markup chain, but I'm not actually recording any of the values, and so that corresponds to throwing those values away, and that's like what we want to do with the burn-in. So the default, as you can see in the window here, the default length of a burn-in in WinBugs is 1,000 burn-in draws from your initial values. And here, actually, because of the adapting approach to the MCMC sampling, a little box is checked. It's actually going to take 500 draws to adapt to try to optimize the MCMC efficiency, and then it'll take the last 500 draws to do the actual burn-in. So that's okay with me. I'm fine with that. So I click on that, and I find that 1,000 updates took less than 1 second, and that finishes my burn-in. Now I go to the inference pull down and choose the samples, create a sample monitoring tool, and now I go ahead and monitor everything I'm interested in. So I monitor mu. Typing in mu as one of the nodes in the graph allows me to click the set button for it. Typing in tau allows me to set that one as well. Typing in nu for that. As I mentioned last time, I could type in y, but that would be a strange thing to do because y is not a stochastic node in the graph. Y is a deterministic node. And it will humor me by allowing me to type in y and hit set, but when it comes to actually running the chain, it will ignore that completely. It will try to politely pretend I never asked for something stupid. So there's no need to put it in. Similarly, there's no need to monitor n, and you can't monitor I even if you want to because it's just a looping variable. But I do want to monitor all sigma also, so I'll go ahead and monitor that, and I also want to monitor y.new. And now I'm ready to do the actual monitoring phase, and here I'm going to use a monitoring period of 100,000 iterations. That's chosen as a compromise between, again, sort of a Goldilocks and the three bears thing. Not enough monitoring iterations, too many, and about right. Not enough would be that you had too much Monte Carlo inaccuracy as a result of not having run the chain very long. Too many would be if it took too long, that we were waiting here to get the answer, and just right is somewhere in between those two. And I have practiced with this model. 100,000 iterations takes about 1.5 minutes, and so that's okay. And I'm going to make it refresh this little iteration box that tells me how far it's gotten in the monitoring. I'm going to make it refresh that every 1,000 iterations so that it doesn't spend a lot of time, CPU time, writing to the screen. And now I'll hit update, and you'll notice that it's turning over pretty quickly. It's doing things at a rate which is actually substantially faster than 1 per second. So, in fact, we won't need to wait anywhere near 90 or 100 seconds here. It looks as though it was able to do all the updating in only 15 seconds for 100,000 iterations. So it's nice to have fast computers these days. As I mentioned to you last time, when this stuff first finally came to the attention of statisticians, the thing I just did would have taken overnight on a desktop machine. In around the year 1990, there almost weren't any laptops yet. And a desktop machine, that would have been an 8-hour run, what we just did, and now it's a 15-second run. So you see that Moore's Law thing happening for us. So now I'm going to minimize the model window and the data window and the initial values window to keep things from getting too cluttered. And I'll now locate the sample monitor tool and the update tool kind of down here, because it turns out that WinBugs likes to pop new windows up in the upper part of the screen for some reason. I don't really need the update tool anymore unless I wanted to do additional updates, but I'll just hold it there. It's okay. So now I go back and see which nodes I remembered to monitor, and there they are. Let's start with mu, which is the one that's the most scientifically important, and I showed you all these buttons last time, but let me show you again. The trace gives you although they've made a bug in WinBugs and it doesn't show you which iterations I think they're roughly the last 500 or so iterations. So it shows you locally in the time series of 100,000 monitored values what the iterations look like. And you can see that that's not exactly like white noise, right? That looks like it has a little too much local pattern to it to be white noise. Then you can do a history of all 100,000 draws. That does look like it globally is mixing okay, although it's pretty hard to tell because I've actually forced it to plot too many numbers on a time series. It's hard to look at the local structure of that picture when there's 100,000 things there. Then I can get the marginal posterior density, and it looks quite a lot like a Gaussian or maybe like some sort of T-curve, centered at about 404 micrograms below 10 grams. And I can ask it for numerical summaries of the posterior. And again, I'll make this a little bigger so we can see it a little more readily. And it reports to me that in this model, the posterior mean is 404.3. So I would conclude that the NB10 block of metal, its true weight is around 404.3 micrograms below the nominal weight of 10 grams. Give or take about 0.47 micrograms. That's my uncertainty band in a statistical sense around that point estimate of the truth. Each of those numbers is itself subject to a Monte Carlo standard error on the order of about 0.002. And so that means that here I have complete confidence in reporting 404.3, and I could have even reported 404.3 blah, where blah is the next digit. I would have been in very good shape for reporting even 5 significant figures on that number there. And I could report the Monte Carlo, the posterior standard deviation as about 0.47. But if I reported 0.469, that would be saying a little more than I actually know, because each of these numbers is uncertain in the Monte Carlo sense down around plus or minus 0.002. And so I'm pretty comfortable with saying that the posterior SD is about 0.47. And moreover, that the 95% posterior interval for the true weight of NB10 runs from about 403.4 up to about 405.2. And then, as I think I mentioned last time, the CODA button, I think CODA stood originally, it's an acronym for something like Convergence Diagnostics. I'm not sure how you very smoothly get CODA out of that, but I guess those letters are in there somewhere. And what happens with the CODA button is that it actually, it creates two files. One tells you what node in the graph is being monitored and what was the extent of the iterations from iteration 1 to 100,000 in the monitoring phase, which I'll kill off because I know already. And the other window dumps out for me the actual sampled draws. And I could now save this file external to WinBugs and read it into R, for example, and do manipulations on it if I wanted to look closely to see whether in fact, the markup chain appears to have reached equilibrium and other things. So There are some diagnostics from this CODA package that I could download from R to run on the chain. In this course, we're not going to worry too much about MCMC diagnostics except for the following things. I'm going to ignore the CODA stuff here. I showed you last time there's this thing called the quantile plot. What it shows you is if we had stopped sampling at 5,000 iterations, what would it have thought the 95% central interval was? If instead it had stopped at 25,000 iterations, what would it have been? And it does that all the way out to 100,000 iterations. So if this picture looks completely unchanged across the entire range of sampling, you have a pretty good visual idea that you were in equilibrium when you began the sampling. And so here I'm pretty okay with that. It's looking pretty good. And then I told you about this. This is a way to I can't press it this time because I didn't run more than one chain. You can run parallel chains inside WinBugs and at different starting points, and that's a way to diagnose whether the posterior distribution is multimodal. I talked with you about that last time. It's in the notes. As a by the way, I said something last time that wasn't quite accurate. I said that MCMC is not that easy to parallelize, and if you were trying to parallelize with respect to a single chain, that's true, because the values that the chain is producing are dependent on each other, and it's not as though you could hand the next task out to 4 different nodes from where we are right now. But here's a simple brute force version of parallelizing MCMC. So this is brute force parallelizing, if there is such a word, parallelizing MCMC. Okay, so on node 1 of my parallel machine, I have a particular random number seed. Random number seed number 1, and I have the same initial values across all nodes, node 2, ... down to node capital N, let's say. But each node gets a different random number seed. And so random number seed 2, ... over to N. They share the same initial values, same initial values, or different, because it isn't going to matter very much. When we're going to same burn in each case. And then at the end, I'm going to get a monitoring chain from node 1 and a monitoring chain from node 2 and a monitoring chain from node ... down to N. And if all of these different chains really were in equilibrium when I started monitoring, then these are all perfectly valid draws from the posterior, and I can just take them and toss them into one big data set, and now that's a really big Monte Carlo sample, MCMC sample from the posterior. So if you have N nodes, and you have an easy way to write, to run one of your sampling engines, you write your own sampler or get WinBugs to run on different nodes or something like that, then you can quickly parallelize what you're doing just by having it do the same thing over again on a bunch of different nodes. And my computer, for example, has 8 CPUs in it, and if I could figure out how to, I probably have to get some software that will actually run program X on node Y. And if I can do that, then I could make this whole thing run much faster. You can do it in R. I would like to hear more about that. If you could email me some details about that, that would be very helpful. Okay, but then the last one, which is another important diagnostic, is the autocorrelation function. And did I describe this to you last time? Did we get this far? So I showed you a moment ago, back over here. I don't think we talked about this last time. If not, even if we did, it bears a small amount of repeating. So take the series and lag it 1 by offsetting it 1, and that gets you rho hat 1. Am I still in the wrong place? Wow. Take the time series in any given column of the MCMC data set, lag it 1 index by shifting it over by 1. So B plus 1 lines up with B plus 2. Correlate, that gives you rho 1 hat. Do that again. Instead it goes B plus 1 lines up with B plus 3. Correlate, that gets you rho 2 hat, because those are 2 lags away from each other. Keep doing that for all the other ones and so on. And so do that as long as you want, and you'll get a whole bunch of autocorrelations at lags 1, 2, and K. And so here I would start with mu star b plus 1 and line it up with mu star b plus 3. And the correlation would be rho 2 hat, and so on. Collect those things together, rho 1 hat down to rho k hat, let's say. That's called the autocorrelation function of that particular time series. Autocorrelation. At least it's the estimated. It's called the sample autocorrelation function. And a very natural thing to do is to plot it. In fact, we could include something called rho 0 hat, which would be just to have the series that starts at mu star b plus 1 correlated with itself, mu star b plus 1. That would be like a correlation at lag 0. But of course, any column of numbers correlated with itself has to have correlation 1, so that's not a very interesting thing to do. But for some reason, people always draw the picture starting at lag 0. So these are lags going this way. And so the autocorrelation function, when you plot it, always has a correlation of plus 1 at lag 0, because you're just correlating with itself. And then you plot at lag 1, you plot the height of rho 1 hat. So this is rho 1 hat there. And then you plot the height of rho 2 hat, and so on. If the series were white noise, so this is what white noise looks like, what would this autocorrelation function look like? There'd be a big spike of height 1 at lag 0, and what would all the other spikes be? They'd all be 0. And in practice, what they would be is little teeny fluctuations around 0. So you'd get a picture that looks kind of like that. And in fact, when you do this in R, and I'll show you how to do that later, R will put some uncertainty bands around this as if there were no autocorrelation. And basically what you'll find is that all those little teeny things that are sort of like little teeny whiskers or something, they're all so small that they don't count. Conversely, or otherwise, what would it look like if, in fact, the story was pretty strongly autocorrelated with itself? Well, there's going to be a spike of height 1 at lag 0, but then the spike at lag 1 might be quite high. This is an example. Maybe I'll show you one where it's 0.9. And a pretty standard behavior when the series is not mixing very well is that it falls down geometrically. So the height of this one here is approximately 0.9 squared, and the height of the next one is approximately 0.9 cubed, and so on. That's called geometric decay, and that represents poor mixing with large rho 1 hat. If the rho 1 hat was small and it still had that geometric decay, then you can see pretty quickly there's not much going on, and this is actually rather good mixing. Good mixing where rho 1 hat is fairly small. So what WinBugs has done for us is it has plotted the autocorrelation function automatically. And you can see that trivial spike of height 1.0 at lag 0. And then the lag 1 autocorrelation looks to be about how big? Look at the picture, what would you say? Plus point what? Plus 0.3 maybe, plus 0.2, plus 0.3. This is an MCMC series that's mixing quite well. When you get a picture like this, that autocorrelation function is not that far from white noise. And so this is good. Everything seems to be behaving well for that parameter. So now I kill off all these new windows I created, and I do the same stuff for the other parameters. So let's pick another one. Let's pick sigma, and I can look at its trace, and I can look at its history, and I can look at its density. And now you see a picture that has a bit of a long right-hand tail. And that's exactly what you'd expect for a parameter that has something to do with scale. It can't go negative, and you expect skewness in distributions for scale parameters. It has an easier chance of being big than it does of being small, and so it has a bit of a long right-hand tail. And here are the stats for it. We would conclude on the basis of this that the population value for the standard deviation, the scale parameter in this model in the NB10 sampling world is about 3.9, give or take about 0.4, and our 95% interval would run from 3.1 to 4.8. And you'll notice this Monte Carlo error is a little bit bigger than the one last time. And that's going to be because when we look at the autocorrelation plot, we can see that the sigma parameter is not mixing as well as the mu parameter was. See how it looks like a ski slope, a sort of geometric ski slope, but the lag 1 autocorrelation is more like plus 0.6, it looks like. Again, that's not too bad. The ones that are really awful, the ones you are scared of, is when it looks like a ski slope that hardly even goes down at all. The first lag 1 autocorrelation is 0.99, and the next one is 0.98, and the next one is 0.97. Then you know you have a really poorly mixing chain for that particular parameter, and you may have to run the chain, either figure out a better way to sample, which is hard because you have to know more about MCMC than we have time to talk about in this class, or else be prepared to sample for 1 million iterations instead of 100,000. I've fit models, I think I may have mentioned this, may or may not have mentioned this to you, involving Bayesian nonparametrics, and later we'll do this, where 10 million to 20 million iterations were needed to get a good idea what was going on in the Monte Carlo sense, because the autocorrelation was so high on some of the things I cared about. So as a ballpark thing to look at as a place to start, 100,000 iterations is always a good place to start for models that update quickly, because then you can see what's going on. And if you look at the picture and you decide you need more iterations because the Monte Carlo error here is too big for you, since you've kept the update tool alive, you can just go back and ask it to get another 100,000 iterations by just hitting the update button again, and it'll start where it left off. And by the way, if you're updating along and it's going too slowly for you and you want to stop it, by hitting the update button while it's updating, that will turn it off temporarily, and then clicking again will start it up again. So you can get out of WinBugs by just stopping it with the update button. Okay, so there's the story for sigma. And the degrees of freedom parameter is interesting. You can see its trace is actually much worse than either of the other traces. That's an example of the kind of time series last time I called sticky, and it's the sort of thing I drew for you a minute ago, where the new chain is not updating itself very much at all each time. You'll notice that it has a bottom value that it doesn't seem to be able to go below. That's because I put a uniform prior on this parameter from 0 to 12. I'm sorry, from 2 to 12, and it's unable to sample below 2 because I told it in the prior it can't go below 2. In fact, in the T model, if I had let that relax a bit and gone down a little lower than 2, it would have been quite happy to sample even further down. But as I told you, I don't believe in models with the T model with degrees of freedom less than 2 has infinite variance, and I don't believe in that as a good model for data. Does it look like my stopping the uniform distribution at 12 has artificially truncated things? Perhaps so, because there are a few draws out of the 100,000 that seem to be bumping right up against that 12 margin. So maybe I should go back, if I were being a bit more careful, and make that number 12 a little bit bigger. Okay, then let's look at the density. The marginal posterior for nu has a whacking long right-hand tail, very skewed, and you can see that also by looking at the summary, the numerical summary statistics. The mean is about 3.6 and the median is about 3.4, and so that's another indication that the distribution is pretty skewed. And you'll notice that the Monte Carlo error for this parameter is much bigger than the other ones. We were getting numbers like 0.002 before, and now it's on the order of 6 times larger than that. And that's because this parameter is mixing the worst of all. The autocorrelation function for it looks like a ski slope where the first order autocorrelation is around, what would you guys say? Around 0.8, something like that. Once again, 0.8 is not a disaster. And you can see already with only 100,000 draws, we have these numbers pinned down with a Monte Carlo error of only about 0.01. But if for some reason you wanted to report to people 4 significant figures on the posterior mean for nu, you can't do it with only 100,000 iterations, because the 3 is solid and the 6 is solid, and already the 2 is a little noisy because the Monte Carlo error is about 0.01. Over here, the 1 is solid, and the 1 is solid, but the 7 is already noisy. So this helps you, looking at the Monte Carlo error helps you to not report more significance than you actually have based upon the length of the monitoring run that you used. And our 95% interval would go from about 2.1 to about 6.6. So that's the story in the WinBugs world. And I think we're meant to take our next break now. So